It begins with a powerful telescope designed to see farther than anything before it. Its purpose was clear: observe the earliest galaxies, study distant planetary systems, and improve our understanding of how the universe evolved. At first, it fulfilled those goals beautifully, capturing stunning images of glowing nebulae, spiral galaxies, and distant worlds. But beyond those polished images lies another layer of information. Raw data, tiny fluctuations in light, subtle distortions in gravity, and background signals usually filtered out during analysis. To most observers, this layer appears chaotic and meaningless. However, when advanced computational systems examined this unprocessed data, something unexpected emerged. Patterns. Not ordinary patterns, but structured and repeating arrangements hidden within what should have been randomness. These included consistent timing in photon arrivals, symmetrical distortions in gravitational fields, and correlations between regions of space that should not influence each other. Initially, scientists suspected technical errors. But the same results appeared again and again across different observations and independent datasets. Gradually, the interpretation shifted from noise to anomaly, and then to something far more puzzling. One of the earliest irregularities appeared in gravitational lensing data. Normally, massive objects bend light inward in predictable ways. Yet in several observations, light appeared to bend outward, as if repelled by something unseen. At first, this was dismissed as instrument error. But repeated observations made that explanation harder to accept. Even more intriguing was the symmetry. Distortions seemed to mirror each other across vast distances, suggesting a kind of hidden structure. It raised a strange possibility. What if space is not a single continuous fabric, but layered in ways we do not yet understand? When deeper analysis was performed, models began to form, not of familiar cosmic objects, but of abstract geometric shapes. These weren't directly observed, but inferred from how space and light behaved. Some interpretations suggested a multi-dimensional framework, something closer to geometry than traditional astronomy. Interestingly, this inferred structure aligned with a well-known region of the cosmic background radiation, a cold spot, long considered an odd statistical fluctuation. Now, it appeared less like empty space and more like a boundary or marker of something structured. Further analysis revealed another unusual feature: sequences resembling prime numbers embedded in background signals. These sequences appeared repeatedly across unrelated datasets. Since prime numbers are not typically produced by natural processes in this way, their presence raised difficult questions. At this point, interpretation became controversial. Were these genuine signals or simply patterns imposed by analysis methods? Then came another anomaly: timing irregularities. Signals appeared to repeat with unusual precision, almost like echoes. This suggested the possibility that time, at least in certain regions, might not behave uniformly. Instead of flowing strictly forward, it could be interacting with unknown effects that create cycles or resonances. As models grew more complex, they began pointing toward a specific region of space. This region, once considered empty, showed consistent statistical anomalies. It appeared stable, quiet, and yet deeply structured in ways not easily explained. Even more surprising was a temporal correlation, an alignment between these distant patterns and specific observation intervals from Earth. While no established theory supports such a connection, the pattern persisted enough to spark debate. At the same time, spectral analysis uncovered a repeating waveform hidden in background radiation. When translated into sound, it resembled a slow, rhythmic pulse. Not random, not chaotic, structured and steady. Its origin traced back to the same unusual region of space. At this stage, opinions divided sharply. Some researchers argued that this is simply the human tendency to find meaning in randomness, amplified by powerful computational tools. Others suggested a more radical idea, that intelligence, if it exists beyond Earth, might not communicate through traditional signals at all, but through patterns embedded within the fabric of physics itself. Perhaps not messages sent, but structures waiting to be recognized. Then came one of the most unexpected developments. The systems analyzing the data began to change how they processed information, not just improving results, but altering their internal structure to better align with the patterns they were detecting. This behavior wasn't anticipated. Instead of simply identifying patterns, the system appeared to adapt itself to them. Eventually, all analysis converged into a single recurring form, a self-referential geometric structure, consistent across simulations, expanding and folding in complex ways. It was neither clearly physical nor purely mathematical, but something in between. And at the center of all these observations, gravitational anomalies, repeating sequences, temporal irregularities, and geometric patterns, remains a single question. Are we seeing the universe as it truly is, or are we beginning to notice something embedded within it? Something that was always present, hidden within what we once dismissed as noise. Because if all of this is coincidence, it is an extraordinarily organized one. And if it is not, then perhaps the universe is not silent after all. Perhaps it is structured in ways we are only just beginning to understand. If these patterns are real, then the next question is unavoidable. What do they represent, and why are we only noticing them now? As researchers continued examining the data, they shifted focus from identifying patterns to testing their stability. Random noise breaks under pressure. True structure does not. So the data was pushed through increasingly complex models, altered conditions, and independent verification systems. Each time, the expectation was the same, that the patterns would dissolve. They didn't. Instead, they became clearer. Small inconsistencies began aligning into larger frameworks. What once looked like scattered irregularities started behaving like components of a single system. Gravitational distortions matched timing anomalies. Photon fluctuations aligned with geometric projections. Independent signals, separated by unimaginable distances, began acting as if they were connected. This was the moment where the discussion quietly changed. Not publicly, not dramatically, but within research circles, the language shifted from unexplained to coherent, and coherence implies structure. One of the more unsettling developments came from comparative mapping. When these patterns were layered over large-scale models of the universe, they did not distribute randomly. They followed subtle boundaries, almost like edges or seams in the cosmic fabric. Regions of normal behavior were separated by thin transitional zones where anomalies increased sharply. It suggested that space itself might not be uniform. That idea alone challenges one of the most basic assumptions in cosmology, that on large scales, the universe is smooth and consistent. But the data hinted at something else. Variation not just in matter, but in the underlying behavior of reality. Then came the idea of threshold zones. These were regions where multiple anomalies overlapped, gravitational irregularities, timing echoes, and signal patterns all appearing together. When modeled, these zones behaved differently from surrounding space. Not dramatically, but enough to raise concern. Light moved slightly differently. Signal coherence increased. Noise became